Hello everyone, welcome to the Lab 5 of ECE573 Advanced Embedded Logic Design. Till now, we have discussed various SDS pragmas, including SDS resource, data copy, zero copy, and access pattern. In this video, we are going to discuss three more SDS pragmas, namely SDS async, SDS wait, and SDS data buffer depth. So in most of the cases, all these three pragmas need to be used together. So first we'll start with the SDS async and SDS wait. So this pragma supports manual control of hardware function synchronization. So when you are calling the hardware function, you need to take care of the synchronization of the data movement between your memory and the hardware function. And this becomes more challenging when you are calling the hardware function multiple times one after the another. So you need to make sure that whenever you are calling the data, whenever you are calling the IP a second time, you don't override the input data which you have passed in the first iteration. So that means you have to wait till the IP completes the operation on all the input data before you send the second set of input data. So as we discussed in the previous lecture, this has been achieved by CF send as well as CF received and the CF wait driver functions. And these are the useful driver function to establish the communication between the memory and the IP in the PL, as well as make sure that the data transfer happens correctly via appropriate data motion network. So using the async and wait, you can do the same thing in the manual fashion. So it is specified. These pragmas are specified immediately preceding a call to a hardware function. Okay. So similar to the SDS resource pragmas, the async and wait pragmas are there when you call the hardware function, that is mostly in the main.cpp file. And they are directing the compiler not to automatically generate the wait statement based upon the data flow analysis. Again, to repeat the same thing, when we discussed the in the previous lab, that whenever you have the CF send, CF receive command, you have the corresponding CF wait command. So here we are telling the tool that you start the sending the data to the IP, but don't wait for the data transfer to complete or the IP to complete the data processing. Just come back to your main.cpp immediately. After issuing all the data transfer requests, control returns to your program, that is main.cpp, enabling concurrent execution of the program while the accelerator is running. So what you are doing it, you are doing the your IP is also running and your processor is now in the next line of your function where it is started executing your main.cpp. So you need to make sure that you use the wait pragma at the appropriate point so that you direct the CPU to wait until the corresponding async function call has been completed. Okay, so what you have done, you have used the async pragmas and you have tell your compiler that you should initiate the data transfer to the IP, but don't wait for that IP to complete the task. Now, after some time, you in your program you want your code IP to finish your operation so that you can make use of that output at certain other places. So how you can achieve that? You need to insert the wait statement on your own at that particular time to make sure that your IP completes your task which was assigned using the async pragma at the wait statement till the at the wait statement, and you will come out of the wait statement after the IP finish the remaining task. So here you can see that every async pragma will require a corresponding matching wait pragma. So if you have the async and there will be ID assigned to you, for that ID you should have the corresponding wait statement. So you can't just give the async and then you ignore the wait statement. For every async, you have to add the corresponding wait statement. So if you use this pragmas and if you check your code, you will see that in your stuff function, you will see that there are only the CF send commands are there, but there for the data transfer, So this is the AXI light transfer. So you can hear it's just a configuration send. So you have the wait statement, but for the data transfer and the data receive, you can see that there is a no corresponding wait statement because you have used this pragmas called as a async pragma. So what are the advantage of using the async pragma, or when we should use the async pragma? Okay, so for assume that you are calling the particular function two times one after the another. Okay, so you can see that I have this mult function. I'm calling the same IP core two times. In the first go, I'm sending the data A and B, and I'm receiving the data C, and then I'm sending the D and F and receiving the output F. So this is different from the SDS resource where we were using the two different IP. Here I'm using the single IP and I'm calling that IP two times. Now, if you don't use the async pragmas, what will happen? You need to send the A, then you need to send the B, then the operation will happen on the A into B and you get the output C, and which will be transferred back to the memory. And after that only your next operation will start, which is the D into E is equal to F. So you can see that your IP is not active all the time. During this time, when the data transfer is happening, your IP is in idle mode, and that is not a good sign, because we need to make sure that our hardware is used most efficiently. It is active most of the time. And that's what we did in the pipelining the IP. We try to use this multipliers and adder. We try to use the utilization of those multiplier and adder. So here we are discussing the pipelining at the IP call level. When we call the IP, how we can make sure that the entire IP is active all the time. So here you can see that by using the async pragmas, what I'm saying, I'm sending the A and B to the IP. Then I am not waiting for the IP to calculate the C. I'm sending the next data D and E to the IP. Okay, so you can see that the data transfer is happening till during the time the execution of the previous data is being carried at the IP level. Okay, and this is called as a pipelining. Another level of pipelining. Here you are doing the pipelining at the functional call level. Obviously here you can see that you need to have the sufficient buffers in the IP, so that when the IP is processing A and B, it is also receiving the D and E, so that he has to have the double the number of memory, double the amount of the memory to store A, B, D, E simultaneously. So that is the requirement is there, but you can see that your performance will get better with this async one. So here you can see that I'm calling this using this async with the ID 1. Then I'm calling this IP. That means I'm sending the A and B, and I'm returning to this one. Then I'm sending D and E. Then I'm returning immediately. Then here I'm waiting for the C to get C operation to get completed and store the C in the memory. And then here I'm waiting for this operation, that is F variable, to get back from the IP and get stored in the memory. Okay, so here what will happen? You will get the improved performance by pipelining the multiple calls to the single IP core. Okay, again here I'm not using the two different IP. I'm using two different hardware. I'm using the single hardware. I'm doing the pipelining to the calls to the single IP core. Okay, and that's how I'm getting the improved performance. What I'm doing here, I'm transferring the input data for the next call. Like I'm transferring the D and E, which is required in the subsequent matrix multiplication, before the execution, before the completion of the C has been done. Okay, so output data from the previous call, that is the C, is happening concurrently with the transfer of D and E. Okay, so that means the amount of the time the IP core spends idle while waiting for the data to be transferred can be reduced. Okay, for example, in the without pipeline case, output the IP is ideal during the you are receiving A and B, And IP is also ideal during the time when you are sending back the C and you are receiving the D and E. So this ideal time can be reduced by overlapping your data transfer with the data execution time. So when the IP is performing the execution of A into B, I am sending the D in E. And when the IP is performing the execution of D and E, I am sending the C back to the memory of your processor. So what is the cost? It requires more memory. Okay, so it allows the it requires more memory because you need to have the more buffer to store the data amount of the inputs and the corresponding output. But what will it will enable? It allows the multiple sets of input data to be passed to the single instance of an IP core without waiting for it to finish the processing of any of the set of inputs. Okay, so you can send the multiple sets of input data before the IP start executing the first set of data. You can buffer all the data inside the IP. The identifier passed to the async. So you can see that as we have discussed, with every async you need to pass the corresponding identifier. It is an argument which specified the queue to which hardware function call request is added. Okay, so suppose you have the IP with the 4 buffers, so your ID can go as a 1, 2, 3, 4. So when you send the ID 1, that means this is called to the hardware function which will execute the data in the buffer 1. When you set the async with the ID 2, you are saying that this is called to the hardware function which will process the data in the buffer 2. Okay, so this identifier is a very important identifier. The number of multiple buffers determines the number of set of input data that can be concurrently passed to the IP core. Okay, so the more the number of buffers is, the more the amount of memory required, but it also gives that the how much sets of input data you can buffer inside the IP. Once all the available buffers of an IP core instance have been exhausted, so that means you have sent the data. Suppose the IP has 4 buffers and you have set the 4 sets of inputs, that means you cannot send the more number of inputs. Okay, if all the things have been exhausted, the program must wait for the IP core to at least finish the first processing of the first set of data. Okay, that is IP core to complete the processing of the input data already in the multiple buffers before you send the new set of the input data. Okay, and this is the logical explanation. The program pauses at the wait pragma. So once you send the, suppose the IP consists of the 4 buffer, you send the 4 data, then you need to make sure that at least your first instance of data get processed. So you add the wait statement indicating that I should wait till I get the first output from the IP before I send the next data to the IP. And this is the use of the wait pragma. Your program pauses at the wait pragma until the next hardware function call request on the queue specified by the argument of the wait completes the execution. So when you say wait 1, that means your first async 1 call should get completed. When you say wait 2, you should make sure that the hardware makes sure that the async 2 call to the hardware function gets executed and completes its execution. Similar to the wait, there is a SDS try wait, and you should figure it out what is the difference between the wait and SDS try wait function. Okay, that is your homework. You should figure it out, the difference between the two. So here I'm giving you the examples how the matrix multiplication can be done using the async and wait pragmas. I think some of the students have already tried using SDS resource, SDS async and SDS pragma. So I think all your doubts regarding why certain approaches didn't work will get clarified from here. So here you can see that I have the one hardware function which has the input A, input B, and the output A. Okay, so this is my hardware function where I have the input A, then input B, and then the output is A. Okay, so you can see here that what I'm doing, this hardware function has the some buffers here. So it has the n buff number of the buffers already. So that means it can buffer those many number of inputs before it start processing the data. So what I'm doing it, I am calling this IP using the async, and I'm sending the data consecutively to this one. So that means I am buffering, I am filling all the buffers in the IP by calling it multiple times using the async pragma. Suppose this number of buffers are 4, so I'll send the 4 set of A, 4 set of B consecutively without waiting for the IP to start execution. Then once I send the 4 set of A, 4 set of B, IP buffers are full. So then I have to wait for the IP to at least complete the execution of the first data. So what I'll do, I'll wait for the first here. Okay. So here, what do you mean by wait here? That I'm waiting for at least one execution of the IP to be get completed. Once I complete the one execution, I know that one of the buffers is empty. So then I'll again call the IP one more time, and I'll send the new data of the IP. Okay. So this will happen depending upon how many times you need to call the IP. That indicates the number of calls. And after you call that IP, then you need to add the appropriate wait statement so that all the remaining executions of the IPs are completed. Because for every async one, there should be a corresponding wait statement needs to be added. Okay. So here the first loop ramps up the pipelining with the depth of the num buff, that is number of buffers available. So you are filling up all the buffers in the IP. Second loop executes the pipelining. So you are sending you are getting the data from the IP, you are sending the new data in the buffer. And the third loop ramps down the pipeline. So you have completed all the calls to the IP, and now you are receiving the data from the IP one, remaining data from the IP one by one, and this is done using the wait statement. Now here you need to have the some sufficient number of buffers in the IP. Again, you need to tell the tool that how many buffers you need in the IP, and then for that there is a pragma called as a SDS data buffer depth. So you need to tell the IP that I need to have this many number of buffers inside the IP. So you need to use this pragma SDS data buffer depth, which we are discussing in the next slide, and this will be set same as to this num buff in your code. Okay, so make sure that when you use the async and wait pragmas, and when you are expecting that your IP should have sufficient number of buffers, you need to add the pragmas to tell the SDSoC tool that please include this much amount of buffer in your hardware IP. If you don't include this, then you will not get the improvement in your performance, because your IP will be created only in using the one buffer. So what is this SDS data buffer depth? It is specified immediately preceding the function declaration. So this is specified in your .h file before you do the function declaration, similar to your data copy and data zero copy. And this pragmas is applied for the interface, which is the either the block RAM interface or the FIFO, because we are talking about the buffers, that is the either the FIFO buffers or the block RAM buffers. So in case of the block RAM buffers, you need to specify the buffer depth and the array size. Okay. So for example, in case of block RAM, you can say that I want 1 buffer, 2 buffer, 3 buffers, or maximum you can have 4 buffer. And each buffer size, number of elements in each array can go from 2 to 16384. Okay, these are the FPGA constraints which are there based upon the amount black RAM constraints. Okay, if you are talking about the FIFO, in the FIFO you can specify what is the vertical size of the FIFO. It can go from the 4 elements in a FIFO to up to 20 elements in the to up to 2 to the 4 elements in the FIFO, that is 16 to 2 to the power 20 elements in the FIFO. Okay, so here you can see that I have the function foo, where my input is a vector of 1024 elements, and the output is a again another b, which we can assume as output is a vector of size 1024. And here what I am telling it is that I want to use the a, here I want to have the buffer for a, and the depth of the buffer is 4. That means I will have the 4 buffers for storing the a. So I can have the 4 sets of a to be buffer in the IP before it start processing the data. Okay, so this is how you can specify the depth of buffer depth in your code. So we have done the most of the SDS pragmas now, and now only 4 pragmas are remaining, which we'll discuss in the subsequent labs. So I'll encourage you to rewrite your matrix multiplication example and add the async and the wait pragmas, and then analyze the performance of that matrix multiplication by using the async and the wait pragmas.